Hey everyone, welcome back to our beginner question and answer series. Today we're exploring the architecture of PySpark, a powerful tool for big data processing. I'm your host and I'll guide you through this fascinating topic. So what is PySpark? PySpark is the Python API for Apache Spark, an open-source data processing engine. It allows you to write Spark applications using Python, making it easier to work with big data. PySpark architecture could be broken down to 3 layers. First is core components. The core components of PySpark include Spark Core, Spark SQL, Spark Streaming, and MLlib, which provide the foundation for task scheduling, memory management, fault tolerance, and machine learning capabilities. Second is PySpark integration. PySpark integrates with Spark Core, Spark SQL, and Spark Streaming to enable seamless data processing, querying, and real-time analytics capabilities. And last is PySpark execution flow. PySpark's execution flow involves application submission, Spark context creation, task scheduling, task execution, and result return, enabling efficient and scalable data processing. In this video, we'll delve deeper into each of these topics, exploring the intricacies of PySpark architecture and how they work together to enable efficient and scalable data processing. First, we have the core components. Let's start with Spark Core. Spark Core is the foundation of Apache Spark, a unified analytics engine for large-scale data processing. Spark Core provides the basic functionality for data processing, including data ingestion, processing, and storage. Key components of Spark Core: 1. Resilient Distributed Datasets, RDDs. RDDs are the fundamental data structure in Spark Core. They represent a collection of data that can be split across multiple nodes in a cluster. 2. Data partitioning. Spark Core partitions data into smaller chunks called partitions, which can be processed in parallel across multiple nodes. 3. Task scheduling. Spark Core schedules tasks called jobs, which are executed on the data partitions. 4. Memory management. Spark Core manages memory allocation and deallocation for data storage and processing. 5. Fault tolerance. Spark Core provides fault tolerance by maintaining multiple copies of data and tasks, allowing for automatic recovery in case of node failures. Then let's talk about Spark Core work mechanism. Here's a step-by-step explanation of how Spark Core works. 1. Data ingestion. Data is ingested into Spark Core through various data sources, such as HDFS, S3, or Kafka. 2. Data partitioning. Spark Core partitions the ingested data into smaller chunks, called partitions. 3. Job submission. A job is submitted to Spark Core, which includes the data processing tasks to be executed. 4. Task scheduling. Spark Core schedules the tasks called jobs, which are executed on the data partitions. 5. Task execution. Tasks are executed on the data partitions and the results are stored in memory or on disk. 6. Memory management. Spark Core manages memory allocation and deallocation for data storage and processing. 7. Fault tolerance. Spark Core provides fault tolerance by maintaining multiple copies of data and tasks, allowing for automatic recovery in case of node failures. Conclusion: Spark Core provides the foundation for PySpark's data processing capabilities. Its key components and work mechanism enable efficient, scalable, and fault-tolerant data processing. Next, we'll explore Spark SQL, another crucial component of PySpark. Spark SQL enables SQL queries on structured data, leveraging Spark's distributed processing capabilities. Key features of Spark SQL are: 1. SQL support. Supports standard SQL syntax for querying data. 2. Data frames. Represents data as data frames, similar to Pandas data frames. 3. Datasets. Provides strongly typed, object-oriented API. 4. Data sources. Supports various data sources, e.g. Parquet, JSON, CSV, Avro. 5. Query optimization. Optimizes queries using Catalyst Optimizer. 6. Integration. Integrates with Spark Core, Spark Streaming, and Spark MLlib. Benefits of Spark SQL are: 1. Familiar SQL syntax, so SQL users can easily transition. 2. High performance, as it leverages Spark's distributed processing. 3. Flexible data processing. Handles structured, semi-structured, and unstructured data. 4. Scalability. Handles large-scale data processing. 5. Real-time analytics. Supports real-time data processing. PySpark SQL components are: 1. Spark session. Entry point for Spark SQL functionality. 2. Data frame. Primary data structure for Spark SQL. 3. Dataset. Strongly typed, object-oriented API. 4. SQL context. Legacy entry point. Deprecated. PySpark SQL operations are: 1. Creating data frames from CSV, JSON, Parquet files. 2. Querying data using SQL syntax or data frame API. 3. Joining data, inner, outer, left, right joins. 4. Aggregations, group by aggregate functions. 5. Filtering, where filter clauses. This concludes Spark SQL. Moving on to Spark Streaming, which enables real-time data processing, continuous data ingestion, and analysis of streaming data, empowering applications. Talking about architecture of Spark Streaming, Spark Streaming uses discretized streams, D-streams, and resilient distributed datasets, RDDs. The Spark Streaming context manages data flow. Key features include real-time data processing, high throughput, fault-tolerant, scalable, integration with Spark Core, Spark SQL, and Spark MLlib. Spark Streaming supports various data sources: Kafka, Flume, HDFS, sockets, Twitter, Akka. Moving on to Spark MLlib. Spark MLlib is a library for machine learning algorithms, providing tools for classification, regression, clustering, and more. Key features include: 1. Scalability, 2. Flexibility, 3. High performance, 4. Integration with Spark Core, Spark SQL, and Spark Streaming. 5. Extensive algorithms. Supported algorithms for MLlib are: 1. Classification, logistic regression, decision trees. 2. Regression, linear regression. 3. Clustering, k-means. 4. Collaborative filtering, ALS. 5. Neural networks, MLP. With help of these algorithms, Spark MLlib can be applied to: 1. Predictive analytics. 2. Recommendation systems. 3. Natural language processing. 4. Image classification. 5. Anomaly detection. That's Spark MLlib in a nutshell. Finally, we have GraphX. GraphX is a library for graph processing, enabling analysis of interconnected data. Its key features include: 1. Distributed graph processing. 2. Graph algorithms. 3. Graph data structures. 4. Integration with Spark Core, Spark SQL, and Spark Streaming. 5. GraphX uses Resilient Distributed Property Graph, RDG, for efficient graph storage. 1. Vertex represents nodes. 2. Edge represents relationships. Built-in algorithms in GraphX are: 1. Shortest paths. 2. Clustering coefficient. 3. Connected components. 4. PageRank. 5. Triangle counting. GraphX can be applied to 1. Social network analysis, 2. Network topology analysis, 3. Recommendation systems, 4. Data integration, 5. Cybersecurity. That's Spark GraphX in a nutshell. Distributed graph processing made easy. Let's dive into the second PySpark architecture breakdown, which is PySpark integration. PySpark integrates with various data sources and frameworks, enabling seamless interactions. 1. Data sources: HDFS, S3, Cassandra, HBase, Kafka, Flume, Twitter. 2. Frameworks: Spark MLlib, Spark Streaming, Spark SQL GraphX. 3. Languages: Python, Java, Scala, R. Its 3 essential components are PySpark Shell. It provides an interactive environment for exploring data and testing code. PySpark API. The PySpark API offers programmatic access to Spark functionality. Its key modules are 1. PySchool, which is Spark's SQL functionality. 2. PySpark.streaming, which is Spark streaming functionality. 3. PySpark.graphx, which is GraphX functionality. Lastly, Spark Session, which is the primary entry point for PySpark functionality. Now let's take a look at the execution workflow of a PySpark application. When you submit a PySpark application, it creates a Spark context, which initializes the Spark engine. The driver program runs on a single node. It coordinates distributed execution, and it creates Spark context. Spark context is the entry point for Spark interaction. It manages cluster resources, and it coordinates task execution. Cluster Manager manages cluster resources, Yarn, Mesos, standalone. It allocates resources to executors. Executors run on worker nodes. It executes tasks assigned by driver and manages data partitions. Data partitioning divides data into partitions. It then distributes partitions across executors, which enables parallel processing, after which driver schedules tasks. Executors execute tasks, and the tasks operates on data partitions. Data transformation jobs are executed like some familiar PySpark operations: example map, filter. It reduces its applied to distributed data, and it then produces transformed data. Let's dive in the PySpark's execution workflow in simpler words. Step 1. Code submission. The user submits a PySpark application. Step 2. Code translation. The driver node translates the code and creates a Spark context. Step 3. Resource allocation. The cluster manager allocates resources for execution. Step 4. Task scheduling. The driver node schedules tasks on worker nodes. Step 5. Task execution. Worker nodes execute tasks using executors. Step 6. Data processing. Data is processed and executors return results to the driver node. Step 7. Result retrieval. The driver node collects results and returns them to the user. Let's now talk one by one on each one. PySpark driver node. It is the brain behind distributed computing. The driver node is the central component of PySpark's architecture, responsible for 1. Code translation. It translates user code into executable tasks. 2. Spark context creation. It creates and manages Spark context. 3. Resource allocation. It requests resources from Cluster Manager. 4. Task scheduling. Schedules tasks on worker nodes. 5. Result retrieval. Collects results from worker nodes. Driver node components are 1. Spark context. Manages Spark application. 2. DAG scheduler. Schedules tasks. 3. Task scheduler. Assigns tasks to worker nodes. 4. Block manager. Manages data storage. Driver node workflow includes 1. Receives user code. 2. Translates code. 3. Creates Spark context. 4. Requests resources. 5. Schedules tasks. 6. Retrieves results. Second key component is the cluster manager. The cluster manager is responsible for managing resources in a PySpark cluster, ensuring efficient execution of applications. Cluster manager responsibilities: 1. Resource allocation. 2. Node management. 3. Job scheduling. 4. Monitoring. 5. Fault tolerance. Types of cluster managers are 1. Apache Mesos. 2. Apache Hadoop. Yarn. 3. Spark standalone. 4. Kubernetes. Cluster manager workflow includes 1. Receives resource requests. 2. Allocates resources. 3. Schedules jobs. 4. Monitors execution. 5. Handles failures. Last component of execution flow is worker node. Worker nodes execute tasks assigned by the driver node, utilizing resources allocated by the cluster manager. Worker node responsibilities are 1. Task execution. 2. Data processing. 3. Resource management. 4. Communication with driver node. 5. Fault tolerance. Worker node components are 1. Executor. 2. Block manager. 3. Shuffle manager. 4. Output commit coordinator. Worker node workflow includes 1. Receives task assignment. 2. Executes task. 3. Processes data. 4. Returns results to driver node. 5. Executor. Executor is responsible for 1. Running tasks. 2. Managing memory. 3. Handles exceptions. That's it for today's video on PySpark architecture. I hope you now have a better understanding of how PySpark works and its benefits. If you have any questions or comments, please leave them in the section below. Thanks for watching, and we'll see you in the next video.